The diagram shows two metal plates. They're connected across a battery, and one of the plates has a potential of V1, the other one has a potential of V2, and they're separated by some distance d. There's going to be an electric field between them that looks like this. The electric field is pointing in the direction a positive charge would experience a force. So if I put a negative charge between those two plates, it would experience a force in the opposite direction to the field lines. The electric field strength can be determined using this equation. Here, electric field strength is equal to the potential difference at the top there. And the potential difference is just the difference in the two potentials that we have there. So V1 minus V2 there. Divided by the distance in meters. For the rest of the equation, I'm going to ignore the delta. I'm just going to do V over D for this equation here. Okay, so the potential difference, it doesn't have to be measured between the two plates. It could be measured any point inside that field as well. So if you do V1 and V2 between these 2 points and you divide it by the distance between those 2 points, then you will get the electric field strength. In this example, the diagram shows two metal plates with potential difference applied across them. So you can see the potential of one plate is plus 200 and the other one is minus 100 volts. Again, the distance between the plates is 5 centimeters. Determine the magnitude and direction of the electric field strength between the two plates. Okay, so the positive plate at the bottom is obviously positive and the top one there is negative. So if I put a positive charge in between, I know it's going to be accelerated upwards. So that's the direction of the field lines. It's going to be upwards. It's going to be attracted towards the negative plate and away from the positive plate. Now, if I want to find the magnitude of the electric field strength, I'll just use this equation. Electric field strength equals potential difference divided by the distance. The potential difference is going to be 200 minus 100. So it's actually 300 volts is the difference between those 2 points. Okay, divided by the distance in meters, so times 10 to minus 2 to 10 into meters. And that gives us an electric field strength of 6,000. And electric field strength is force per unit charge, so it's newtons per coulomb. Okay, part B of this question, complete the graph of electric field strength E against the vertical distance from the bottom plate X. So basically, how does electric field strength change as you move away from the bottom plate there? It's a trick question. It's because it's a uniform field. The electric field strength is going to be the same everywhere between those 2 points. It's what we calculated a second ago is 6,000 newtons per coulomb. So it's just a straight horizontal line like this. Example 2. Show the acceleration of the particle with mass m. So I'm going to annotate this information onto the diagram as we go through it. So we've got a particle here with mass m, charge q. The potential difference between the parallel plates is v, and it's separated by distance d. Okay, and we need to show that the acceleration is given by qv over md. So it's going to accelerate. For example, with a positive charge particle, it would accelerate towards the right. Now, in order to find the acceleration, we have to find the force on the charged particle. So we're going to have to find the electric force. We're going to ignore all other forces on this charged particle, just the electric force. And that's going to come from the electric field there. So we can find the electric field strength first by doing V over D, and because we've got the potential difference, we've got the distance. How do we get the force from this? So the electric force is going to be the charge times electric field strength. So if we multiply everything by Q, we get the force. Okay, after that, from force we need to get acceleration, and we know through Newton's second law, F equals ma, that if in this case if we divide the force by m, we'll get the acceleration. So in this case, I'm going to put ma equals qv over d. Okay, so then I'm going to divide both sides by m, get the acceleration like this. Okay, now once I've got the acceleration, I can actually just use Suvat's to calculate how fast it's going, the distance traveled, and so on. For example, v squared equals u squared plus 2as. Okay, in this final example, a stationary electron is placed between two parallel plates as shown. The distance to the negative plate is a quarter of the plate separation. The potential difference between the plates is 10 volts. The electron accelerates and exits through a small gap in the positive plate. Calculate the velocity of the electron. So it's initially stationary and it's going to speed up through that gap like so. Now it's important to notice that the electron doesn't actually travel the whole 10 volts worth of potential difference. It only goes through a quarter, 3/4, which that means it only goes through 7.5 volts. Now potential difference, if you remember from year 12 physics, it's work done per unit charge. I'm actually going to use lowercase q here. Okay, so if I do the potential difference times the charge, I get the work done, like so. And in this case, the work done is the energy gain, the kinetic energy gained. So I'm going to replace that with half mv squared. Okay, I'm going to move the 2 to the other side, and I'm going to divide it by m, and then I'm going to square root it. Now, this is a very useful equation, also known as sometimes electron gun equation, really worth memorizing. Okay, that can give me the velocity it exits at. So I'm going to do this 2 times, a square root of the 2 times the charge, and this is an electron, so it's just 1.6 times to the power minus 19. Potential difference it moves across, which is 7.5 volts, divided by the mass of an electron, which you can get from your data sheets, 9.1 times 10 to the minus 31, and that gives me a speed of 1.6 times 10 to the 6 meters per second, which is below the speed of light, so that makes sense.